Okay, so let us now start this next section, Riemann integrability of continuous functions. Let's think of what we have done so far in integration. We started off with the class of piecewise constant functions. We first learned what it means to integrate them, and then from that we generalized to the notion of Riemann integrability of bounded functions. We also proved some properties of Riemann integrable functions in the previous section, and we have also already seen that the class of piecewise constant functions also turns out to be Riemann integrable. That means each function in that class is Riemann integrable according to our general definition of Riemann integrability of bounded functions. But so far, apart from the piecewise constant functions, we haven't really seen any other Riemann integrable function which is, say, not piecewise constant but something more general, say a general bounded function which is Riemann integrable. And this is the time we do so, that is, we now want to enlarge the class of Riemann integrable functions from only piecewise constant functions to something larger. Okay, so in that direction, this is one step. We want to see how continuous functions also are Riemann integrable, and continuous functions need not be piecewise constant. Piecewise constant functions in fact are really not continuous. I mean, they have breaks, but we will see where this thing is going. So in this section we are going to see how, if parts of a function are continuous, just like piecewise constant functions, there is a notion of piecewise continuous functions. Such functions we will ultimately show are also Riemann integrable. But we will start off with something else, uniformly continuous functions. So let's start with this theorem. This is the first item of this section. So it will be 11.5.1. And the statement is this: let I be a bounded interval and let f be a real valued function on I, and let it be uniformly continuous on I. Then f is Riemann integrable over I. Okay, I is a bounded interval, but it's not said whether I is a closed interval or an open interval or a half open interval. So all possibilities are there. F, however, is uniformly continuous on I. Then we have to prove that f is Riemann integrable on I. All right. Note one thing, that because I is a bounded interval and f is uniformly continuous, so f is also automatically a bounded function. Alright, this is not necessarily true for just a continuous function. If the interval is not a closed interval, say it's an open interval, and the function is just continuous, not necessarily uniformly continuous, then it's not necessary for f to be bounded in that interval. For example, you can think of this function, say this function. It is continuous but not uniformly continuous, and it's also not bounded. The closer your x goes to 0, the higher the value of the function becomes without any bound. It gets arbitrarily large as you take x closer and closer to 0. And by arbitrarily large, we mean that no matter how large a real number you choose, the output can be made even larger than that by choosing x sufficiently close to 0. Okay, so it's not necessary that such function will be bounded even if it is, it's of course continuous. Why? Because it is a rational function. It's a quotient of two polynomial functions, and polynomials are known to be continuous, and the denominator never becomes 0. Okay, but if you have uniform continuity, then over bounded intervals you have a bounded function. But anyway, let's now see the proof. That means we can talk about Riemann integrability, because if your function is not bounded, then forget about Riemann integrability. And in the proof, we first consider the case where I may be degenerate, that is, I may be empty, or I may be an interval which has only one point. If I is empty, or I is a singleton set for some real number a, then f is obviously Riemann integrable. Why? That I leave to you. Let me just tell you one thing, that when I is a singleton set, then our f is automatically piecewise constant, and piecewise constant functions are already Riemann integrable. We have proved that before, and that's why this case is settled. I want you to think about this case. This is also something similar, but you need to think of it carefully. But in this case also f is Riemann integrable. So now we can assume that our I is a bounded non-degenerate interval. Okay, so it's not like this, not like this. Now assume that I is of the form a comma b, or now all the possibilities will have to be considered. This or this or this for real numbers this. Actually, we should write for real numbers a and b such that a is less than b, but sometimes for brevity we write like this, and it's understood what we mean. For real numbers a and b, like this. Okay. Now choose any arbitrary positive real number epsilon. Okay. Now immediately we are going to use the fact that f is uniformly continuous over I. So from that, for this epsilon, let me just write the reason also. Since f is uniformly continuous on I, there exists a delta which is positive such that, so here we are just going to write the definition of uniform continuity, such that the distance between the f values of x and y is less than epsilon when x and y belong to I and the distance between x and y is less than delta. Alright, so we let it sit like this, and now we do something with this a and b. Note that because a is less than b, b minus a is a positive real number. So by the Archimedean principle, there exists a positive integer n such that b minus a divided by n is less than delta. B minus a is positive. In simple language, you can choose capital N large enough so that when you divide b minus a by n, it will be less than delta, no matter how small delta is. Okay. And rigorously, of course, this comes from the Archimedean principle. Alright, now what we do, we will now partition our interval I into subintervals, n subintervals. Each one of them will have to have this length. This is a positive real number, right? B minus a is positive because of this inequality, and n of course is a positive integer. So this is a positive real number. So it makes sense to say that of length this. Okay. Now we partition I into n, not this then, sorry, n intervals J1, J2 and so on, Jn, each of length this. Let's give this some name also, say J. but the question is how. Note that our I actually can take one of the above 4 forms, and depending on what form it has, the partition will change slightly. The author does not really provide us with a concrete answer to this, but he asks us to treat these 4 cases separately. It's nothing really that difficult. Let's just see it for the which one should I choose? So let me choose this one for this interval. How do we partition this interval into capital N intervals, each of that length? It's pretty easy if you think about it geometrically. But anyway, let's just see that. And the other cases I will leave to you. Note that all these 4 cases come from the possibilities of having or not having these n points of the interval within the interval. So let's just see the case for the closed open interval. So this is supposed to be not a part of the proof. So we have this interval. How do we partition this? What I do, I start with this left hand side, taking A within the first subinterval, that is J1. Now I want to make this interval one whose length is what? J. So obviously what should I do? I add J to A. That's it, then its length will be A plus J. If you think why I chose this side to be open, it's to maintain some kind of uniformity, and the pattern will be like this. The next one, J2, is this. Oh, and keep one more thing in mind. Because we want a partition, the subintervals should not intersect each other. Okay, they should have empty intersection pairwise. Another one, if you want to write, it will be A plus 2J. So that's why if you keep this side open, you keep this side closed. And one more thing is that besides being pairwise disjoint, they have to cover the entire interval I fully. When all the subintervals are taken into account, their union should be equal to I. Like that it will go. And finally, if you okay, so what should the final one look like? That's the question, no? I mean, if you follow this pattern, that pattern itself will answer you what this final one should be. The final one should have B on this side. However, the pattern says that this B needs to be A plus something times J. So if A plus something times J needs to be equal to B, then what should something be? That something should be equal to B minus A divided by J. But what is J? From this equation we get B minus A divided by J is N. So this something is actually nothing but N. Okay, so there is no need to, of course, write A plus Nj here, because that is just B. But then what is the previous one according to this pattern? What the pattern says is that whatever you have here, you have to have one less than that here. So that means this end is this. A plus N minus 1 times J plus B. And here you can see that these intervals form a partition of our I, if our I is this. Okay. Let me just keep this one also here. So that way we can partition I into n subintervals, each one of length j. And the other cases, of course, you can handle similarly, because you understand that you can basically do the same thing, just you have to adjust these endpoints. And in fact, if you had this side also open, there will be only one thing that you have to do in that case. You just keep this side open. That's it. And similarly, the other cases also. Okay. So that means it can be done. All right. Now, what are we going to do with this partition? We are now going to use this partition to talk about upper and lower Riemann integrals of f. Essentially, we want to just prove that these two integrals, upper and lower Riemann integrals of f, are equal, because that just means that f is integrable. All right. And this is a point where we have to go back to a result which links these integrals with upper and lower Riemann sums. Now we are not going to use the actual definitions of upper and lower Riemann integrals, where we use integrals of piecewise constant functions. Forget about that thing. You go the usual way with Riemann sums, and we are going to use proposition 11.3.12 for this. So let me continue from here. Now, by proposition 11.3.12, what does that proposition say? It says that the upper Riemann integral of f is the greatest lower bound of all the upper sums, and the lower Riemann integral is the least upper bound of all the lower sums. Upper sums and lower sums of f with respect to what? With respect to all possible partitions. Now, these j's provide one partition. Okay. So, with respect to this partition consisting of these j's, you get one upper sum for f and one lower sum, because the upper Riemann integral is the greatest lower bound of all the upper sums. So, for this partition, the upper sum that you are going to get, the upper Riemann integral will be less than or equal to that. So, let us first write that. Okay, so the upper Riemann integral of f over I, because it's the GCD, sorry, not GCD, but GLB. I went to somewhere else. GCD, it's not GCD, of course. So it is less than or equal to that particular upper sum, which will be this f of x, x belonging to jk times the length of jk. You see clearly what this is. This is nothing but your uf comma p, if p is that partition consisting of the ji's. Okay. So, you get one inequality, and of course this is what upper sum is. Each term has the supremum of the function values over that subinterval multiplied by the length of the subinterval. In fact, let me use another set of parentheses. Just like that, the lower sum of f over I by not by definition but by that result, by this result, is the least upper bound of all the lower sums. Because it is upper bound, we have this inequality. In particular, it's greater than or equal to the lower sum of f for that partition times the length of Jk. Alright. So if we now use these two inequalities together, then we get this. Thus, the upper integral minus the lower integral is less than or equal to, see, negative of this is less than or equal to the negative of this. And that's why, and then if you adjust the sum, ultimately everything comes down to this. Supremum of f of x minus infimum of f of x as x varies over the interval Jk multiplied by the length of the interval Jk, and the sum is it has these terms where k varies from 1 to n. Alright. Our aim is to show that this difference is exactly equal to 0, but it is less than or equal to this. But how small is this sum? Okay, that now we have to figure out. So now we bring back epsilon and delta that we let hanging there. Okay, we left there hanging, which comes from the uniform continuity of f. We are now going to see what the difference of f of x and f of y is if x and y both come from Jk, where k is any of these values. Okay. Now let x and y be any points in Jk. All right. Then the distance between x and y obviously should be less than or equal to the length of Jk, because if the length of the subinterval itself is something which we already know, which is our small j, then the distance between 2 points coming from that subinterval cannot be exceed that length. Okay, it has to be either equal to that length if the 2 points are the two ends of the subinterval, otherwise it will be smaller than that. So in general, it's less than or equal to j. And note that this is j no matter what k is, because all our subintervals are of length fixed that j, which is b minus a divided by n. Okay, and we already have chosen n in such a way that this is less than delta. And are these x and y in capital I in our original interval? Of course, because this is Jk is a subinterval of I, so it's a subset of I. So x and y both belong to I, as well as this is less than delta. Hence, this is less than epsilon by our previous condition. In particular, we have this, or this. Now note that our choice of x and y are really arbitrary. I mean, we are choosing these points from Jk, but they can be any points from Jk, and they do not really depend on each other. I can choose whatever x I want to choose, I can choose whatever y I want to choose, and my choice of x does not influence the choice of y or be influenced by the choice of y. They are independent choices. So now I can change x. For any chosen y, I can keep changing x. I can take any x from Jk for any chosen but fixed y. And that is why from this inequality we next get this. Note that what I am going to get if I change x. If I keep y fixed, then this f of y plus epsilon becomes an upper bound for all the f values as x varies over Jk. Obviously, because you can take any x here, this doesn't change. Once you have chosen y, this stays fixed. So for all such f of x, this becomes an upper bound. So the least upper bound or the supremum of all these f of x's as x changes over j of k will be less than or equal to this upper bound, because it's the least upper bound. I mean, that least upper bound may be this also. That's why we keep the possibility of equality. In other words, I have now this. Okay. However, what we have got here is in fact true for any y as well. I mean, when transitioning from this inequality to this one, y was fixed, but any y. Now we can change y as well. Now note that the left hand side really does not depend on x. It's a fixed quantity. And that's why this now becomes, well, not exactly this. Let me write one more line. Or let me subtract epsilon from both sides. Yeah, now we are there. Now the quantity on the left hand side of this inequality is independent of x, but that's not the point. It does not depend on y, it does not change as y changes. So this quantity now becomes a lower bound of all the f values as again y varies over Jk. So this is one lower bound. The greatest lower bound will be obviously greater than or equal to this lower bound because it's the greatest. This then implies that so this one lower bound is less than or equal to the greatest lower bound or infimum. Alright, now we will again switch sides. Switch sides means we will send the epsilon to that side and bring the infimum to this side. Or, now I am going to write something which may suddenly confuse you. What happened to y? In place of y I have written x. Can I do that? Well, I can do that. I mean, the way we started this calculation with x and y, there you cannot just simply write x in place of y, because those are two um, arbitrary choices from JK, two arbitrary elements. However, remember I said that this quantity does not really depend on x. I mean, it does depend on x, but not in that way. The way those choices x and y depend on x, because they are the choices. Here, however, it does not really matter whether you write x or y here or something else. Whatever name you want to give to this dummy variable, the quantity itself does not change. So that's why here in place of y I can write x, and I have decided to do that because this is how we have the difference in that sum. Okay, so now use this information to our previous inequality. Hence, the upper integral minus lower integral, which is, let me first write what it was. Minus infimum times the length. Don't forget the length. Okay. Okay, so now what we get, regardless of what k is, this difference is less than or equal to epsilon. That means this entire sum would now be less than or equal to this. And the epsilon, being independent of the index of summation, comes outside of the summation. One of the properties of finite series allows you to do that. And now this is just the sum of all the subintervals, because they form a partition of our original interval I. So it will be the length of the entire interval I. And this is one result that we proved way before, and it's theorem 11.1.13. We can write here by theorem 11.1.13, and this actually is this. Now, in the beginning itself, after making the choice epsilon, instead of working with epsilon itself, you could have worked with epsilon divided by b minus a and treat it as a new epsilon. And whatever you did for epsilon, you could have done that for that epsilon. Say you call it epsilon prime. But of course, that does not really change anything. So now you have this. You know that because your function f is bounded, so these upper and lower Riemann integrals are also bounded, and in fact the difference is greater than or equal to 0, but it's less than or equal to this quantity where b minus a is of course positive and epsilon is our choice. So now you know what to write, since epsilon is arbitrary and positive of course, and b minus a is positive, we have, means we must have that this has to be equal to 0. This cannot be positive. Otherwise, if this is positive, then so small an epsilon can be chosen that this becomes less than this, which will then go against this entire thing. So everything will be contradicted, and that's why this cannot be positive. But then, because of this inequality, it can only be 0. Uniform continuity has helped us to get this result. So we have this or this, hence f is Riemann integrable, and that completes the proof. So now you know that not just piecewise constant functions but uniformly continuous functions over defined on bounded intervals are also Riemann integrable. Okay, but uniformly continuous functions still do not really sound that nice. I mean, they are there, but uniform continuity seems like a stringent condition. But now let's see the next corollary, which will ease something. I mean, it will at least help you recognize that yes, many functions are indeed uniformly continuous if they are defined on closed intervals and are continuous. So this is corollary 11.5.2. Let without writing it like this, let me write like this. Let a and b be real numbers, and let f from closed interval equality. This time our I is not anything like that, it's closed interval. Be a continuous function. Then f is Riemann integrable on I, of course, and you will almost immediately see why that is so. And the proof depends on a previous result, which is theorem 9916. By theorem 9916, f is uniformly continuous. Now apply the previous result. That's it. There is one small thing here though. I mean, if you really want to write a formal proof of something, you should not really skip simple steps. I mean, some authors do this. but that just make things somewhat unnecessarily complicated. What I am trying to say here is that, note that I haven't said that A has to be less than B or greater than B. A may be greater than B. In that case, this closed interval is empty in fact, but still it's an interval. It's a degenerate interval, and in that case we already know that integrability is there. Even when A is equal to B, this is degenerate and has only one point. So those cases you should actually write in the proof, and you should dispose of those things in the beginning itself and then get to the main thing. And from this theorem, which we already saw before when discussing uniformly continuous functions in the chapter on continuity, that's the 9th chapter, we saw that if a function is just plain continuous but the domain is closed interval, then it's automatically uniformly continuous. So by the previous result, it's integrable. Okay, so let's just end the video here itself. There are some other things. In fact, we have to go to that part which says that not just uniformly continuous or continuous functions like this, but piecewise continuous functions are also Riemann integrable. Okay, so those things will come afterwards. So we will see those things in the next analysis video. And tomorrow also we have one upload. Let's do number theory tomorrow, and tomorrow we will start Fermat's theorem, that chapter. So with that, let me just end things here itself. So see you tomorrow with number theory. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.